comparing DESI and supernovae results, not only Pantheon but other supernovae collaborations for omega M and so on, because I've seen results where these differ quite significantly, and sometimes they're combined for example, the whole evolving dark energy thing, and I was wondering if you could comment on that.
I think you asked something about the different supernova data sets that are used when people look at the DESI results and evolving dark energy. Is that the question?
It's about that, but also about how the compatibility of using those data together because of the, for example, them suggesting different omega M values, so different matter density values between the DESI and the supernova data.
So you're asking if supernova data is consistent with BAO data?
Yes, for example, in terms of the matter density.
Yeah, well, I mean, there's right, if you look in the context of lambda CDM, then supernova data and BAO data look like they're pulling in opposite directions a little bit for omega matter. So you have, CMB data wants around, 0.32, supernova data wants around more 0.35, and I think BAO data wants more like 0.29. But again, that's part of, this is like, when you have, you're carrying a bunch of laundry in your arms and you can't keep it all there, and you drop one piece and you try to pick up another piece and you keep dropping something else. Lambda CDM doesn't fit all three data sets right now. And so if you force it to fit them, then you will see some slightly different parameters for the different, like supernovae versus BAO. This is just a manifestation or a restatement of the problem. When you introduce, some kind of non-lambda dark energy, then it tries to, this thing of seeing different omega matters in lambda CDM now becomes part of the signal of seeing evolving dark energy. But this is all around the 3 sigma level. And so, we're unsure, what's the right story. People keep asking me about the evolving dark energy, and I say, I don't take literally evolving dark energy or that particular model. What I take from it is lambda CDM is not fitting all three of these data sets well. There's some tension there, and that's very interesting. I don't know what it means, but I wouldn't go to just, well, it's evolving dark energy. It's something that, again, it's assuming it holds up statistically, that is not fitting lambda CDM well. So I'm more keeping track of cracks in lambda CDM rather than maybe taking each one literally as it says this, because I don't think the data is good enough to say yet what they say.
So would you say that apart from like the Hubble tension that people talk about between like it's very CMB, so Planck versus supernova, would you also say that there is sort of a BAO tension between the supernova and the BAO that maybe should be a little more discussed? Or
there's some tension between BAO and supernova in the context of lambda CDM. There's also tension between BAO and CMB in the context of lambda CDM. I think yesterday with the
Okay, so Katie, I think you want to add something.
So I was just
excuse me? There's a 3.7 sigma difference between the CMB and BAO in lambda CDM right now.
Thank you.
I wanted to say something about these latest claims of the DESI experiment about a time varying dark energy. The reason they're getting that, and I think Adam, you mentioned this, or somebody did, is the W0 WA parameterization. So they're taking this equation of state. It's, if you do a Taylor series, you take the z equals 0 value, and then you take the first derivative, and those are the only two. If you fit with only those two parameters, it's going to give you the wrong answer. And so we did the simplest thing in the world, which we advocated for 20 years ago. This is Yun Wang's idea, that you go directly from the data to the energy density as a function of redshift, the dark energy density as a function of redshift. And if you do this, then we only have a 1.5 sigma discrepancy with lambda CDM. So it's simply, and actually in the DAISY paper, they did something almost the same as ours, but they thought of it as confirming what they got with their other approach rather than looking at it directly. And So energy density directly is the way to go. It's better than going after W in the first place, and certainly not a simple parameterization like that, which gives you very weird answers when you go to any decent redshift at all.
Well, there is any question for Professor Mukhanov? Maybe?
Related on what's
Okay, please.
I just would like to add a comment that Professor Mukhanov has mentioned about the data. So in 2001, KITS has announced this sigma 8 tension, and in 2025 data, the sigma 8 tension has gone. So the reason is systematics. Now, Adam Rees has mentioned in his talk that about George Estacio, he expressed concern in a recent paper about evolving dark energy or systematics. So I'm wondering, I would like to hear from you. The KITS data is the best example. In just 5 years it disappeared. So I'm wondering if Hubble tension will disappear with more understanding of systematics, supernova systematics.
First of all, it's to me, I will profit. Second, I'm not astrophysicist. Yeah, and then second, actually, I observed in my life so many crises in cosmology, kind of animation. Okay? Super radios. Global cluster. 130 megaparsec periodicity of the distribution of the structure. Then, upper bound on the number of neutrinos from nucleosynthesis smaller than 1.7. What else was there? It was by Blackman and company, as you know. And then everything goes, goes, goes. G minus 2, yeah. So, therefore, okay, and I think the problem is systematic, is not fully settled, everything could come and could disappear. Right now, Adam claims that he knows systematics, Wendy claims that systematics is much larger. Yeah, so whom I should believe? I should not believe to anybody, because the problem of Hubble tension should be first solved within the Hubble tension itself, yeah, in this sense. And why we are sure that supernova are so perfect standard candle, it's another question, because they have even peculiarities within subclasses. Who knows? We will see, but it can take a lot of years. But it's not so relevant for early cosmology, as I said. Also, from CME data, I believe that people exaggerated accuracy. Why? Because normally in CME data, omega always comes in combination with omega h squared. There is only one place where the thing is degenerate, when you fix omega total to be equal 1. Then the degeneracy is extremely weak. It's like omega h cubed, but in power 0.16. Therefore, in my book, I wrote that fixing the location of the third Doppler peak with accuracy 1% would allow you to measure Hubble constant from CMB data with accuracy not better than 7%. What they present right now is quite surprising for me, but you understand it's all done with big calls when the people are trying to minimize error bars for all parameters, relevant, irrelevant, etc. without separating or discriminating relevant parameter from irrelevant. You see? So I don't know.
Okay, so I would like to ask Professor Adam Rees to comment on the KITS data and also about the supernova systematics that George Estacio is pointing out.
Can I answer this question?
Yes, please,
Yeah,
Adam,
okay,
go
good.
on.
Yeah. I mean, it's very interesting, right? We can play historians and say, look, this tension went away. But on the other hand, there's a whole set of things that stay and we discover things, right? So, I would say don't get old, because as you get older, you become cynical and you say, oh, I've seen this, oh, I've seen that, but you know, this subject is science, it's not history. And so you have to look critically at the current data that we have, because if you look at history, the answer is sometimes things are real, sometimes things are not. You know, if you're going to do the science, you have to look critically at the data. Say, is this experiment mature? Do I see it many different ways? Is this the best data that we have? Has it grown in significance? Has it been seen with multiple facilities? So, you know, there's no substitute for looking at those elements, because otherwise we fall subject to confirmation bias, that you say, well, here's what I think is going on, and then whenever the data doesn't fit that, you say, that'll go away. And when the data fits what you think, you say, that's the right answer. And so, you know, we need to be very, very careful to, as I said, not become cynical and use history. I mean, I can tell you this wonderful story about how, you know, the precession of Mercury was seen for decades, and people doubted it because it didn't fit Newtonian physics. And that's the archetype example of, like, it was new physics, and that was very exciting. But, you know, the problem is you can't use history as a guide. So you have to ask yourself, are these really good experiments? Have they been around a long time? Is the data public? Has anybody found a problem? And, you know, are these our first-rate tools? And if you see a result that doesn't make sense to you, if you're going to blame the experiment right away, then you never really were doing experiments to learn about nature. You were probably just using them to confirm your prior. And so I think we have to be very, very careful about that. I think the current tensions that we see are very interesting, and they're worth studying because they're the best chance you have of seeing something new going on.
So Adam, thank you for giving us tensions to play with.
Sorry, Kitty, the time is really running, so there will be a question from a very young student. If the organizer allows me, I will take that last one.
Here, you can take.
I mean, from the guy over there. Microphone? Okay. And then this is the very last one. Unfortunately, the time is really out.
Yeah, I'll try to keep it.
No, we can go and they can take question from the students.
Just 2 minutes and we go. I'll try to keep it short. It's actually a question for Slava. If he has any comment on the cosmological correlators program and anything related to his talk about that.
You mean cosmological correlated programs? It's about 3-4 point correlation.
Yeah,
right?
for example, and how you can connect it to.
No perfect, it's enjoyable calculation if you enjoy by itself, but I don't think that you can ever be able to relate it with any measurement, you see. Because already 3-point correlation function is undetectable, because, you know, as I said, we live in finite universe. If you would be able to apply with the infinite number of universes, then you could measure there any correlation function.
Okay, Slava, I think has to go, so you need to leave us.
Yes.
Shall we start? Okay, we close here. Thank you very much to everybody.